Hello, welcome again to our lesson number 5. So in lesson number 4, we started to look at the voltaic cell or the electrochemical cell, which I gave general example and I set up there for zinc copper half cell. So in this lesson, so we are going to see how now to set up that, and finally how to represent that on the drawing the cell diagram, the cell representation, and discussion on observations, what will be observed during the course of that setup if we leave it to run for quite some time. And then generally we should now be able to predict when we connect different half cells what we will observe at the positive electrode and at the negative electrode and what are they called. So that's what we are going to discuss. So to start with, so there is the setup that I've made for that electrochemical cell, which we ended up with lesson number 4. So we are in lesson number 5. So this is the setup. So here we have the zinc chloride solution, and then inside I have placed the zinc plate, and then here we have copper 2 sulfate solution. Then inside there is copper rod there inside the solution. Then this is the voltmeter reading, on which we have seen that on the voltmeter the reading is 0.9 volts from our connection. So this is how you set up. So you need a solution containing zinc ion, zinc nitrate, zinc sulfate, zinc chloride. So I've used zinc chloride. Then also a copper solution, solution containing copper ions. Then when you connect, then the salt bridge. So there we have the salt bridge. So we have the cotton wool at the end, which helps to contain the salt solution inside, and also it is a good absorber, so it will absorb most of the solution. So this is how to set up. Now let's see the workings on it now. In the theory, in the practical exam, you will not be asked to do this practically, but this question comes in the theory. Now, like for example, the blackboard there, on the whiteboard, I have indicated how to or making an electrochemical cell using zinc half cell. So this will be the representation, because sometimes in exam can just be given like that. So that is how to represent the zinc half cell. So this is the rod, the metal plate, and this is the solution. So like now what we have there, that half cell. So in this case, this is the solution, this is the plate. So when you place them like that, so this, what we are calling zinc solid, is this one. Then zinc aqueous, it is this solution. Then on the other hand as well, the copper half cell. Now what we are having as the copper solid will be now this metal here, and then the aqueous, copper aqueous, to be referring to copper 2 sulfate solution. So that will be now the practical aspect of it. Now let's look at the theoretical aspect of that. So theoretically now, this is how you will set up the setup. Then, as I said, always start with the more reactive followed by the less reactive. So on our left, this should be the zinc half cell, and this should be the copper half cell. So you have to label it, don't assume. So this will be the zinc solid. So on the half cell, this is now that part, the zinc solid. And then now, inside now the solution, this one, the solution now, this is where you have, now like the solution I used zinc chloride. So you can have the entire formula of the solution, zinc chloride solution, or you can even just write the anions only, which is this part here. Here the anions are not very important. So zinc ions like that. So that is a solution containing zinc ions. So it can be zinc sulfate, zinc chloride, zinc nitrate, whatever. Soluble zinc salt. So it has to be a soluble zinc salt. So we cannot use zinc carbonate, because zinc carbonate is insoluble. So the solution that you are going to use there, so you have to put that into consideration. It should be a soluble salt. So there you refer to solubility rules to know which salts are soluble. Then this is going now to be the copper rod or copper plate. So the solid. So this which is this part here, copper solid, and then this will be copper 2 sulfate solution. And as I said, this anion is not very important, so you can even write without. So if you write copper 2 sulfate, still it is correct, or without, still it is correct. Like that. So that is a solution containing copper ions, which in our case we have used copper 2 sulfate. Then this is the salt bridge. So for my practical setting, I have used sodium chloride because the chloride ions will not affect the copper ions. Copper chloride is soluble, zinc chloride is soluble. And that is why I have used this. And then all sodium salts are soluble, all potassium salts are soluble. And that is why the choice here is either sodium or potassium. And usually here, to be on the safer side, you can always use a nitrate because all nitrates are soluble. So you are very sure that your salt in the salt bridge will not precipitate your ions in either of the half cells. So once we have that set up, this is now the salt bridge. Now we have the cotton wool, as I've indicated there on the setup at the start of this lesson. So the cotton wool, if you have used the glass, the U-tube glass, you have to use the cotton wool to prevent the solution from pouring out when you invert the salt bridge in the beakers. But otherwise, you can also improvise, like what I have done there. I've just improvised using a filter paper and also cotton wool at the end of each end, and still it works. Then connecting wires, as you have seen, through the voltmeter, and then from our voltmeter reading, our reading is 0.9 volts. But the theoretical value when you connect these two, you are supposed to get 1.10 volts. This is the theoretical value. Usually during the practical, you don't get that exact value, and the reason is because of the resistance in the connecting wires. And if we were to use the switch, if we were to incorporate even the switch, this voltage could then drop much lower because there is also resistance in the switch that has to be overcome by the current. So the reason why we have not gotten 1.1 voltage is because of the resistance in the wires, which has to be overcome by electricity. So at the end result, the voltage obtained is less. So this will be how to represent this half cell. Then you can be asked to write now the cell representation of this. So this is now the electrochemical cell for zinc half cell and copper half cell. Now the cell representation for the same, if now you are asked to write the cell representation for this. So we start with the most reactive, which is zinc. So zinc solid, zinc aqueous. So the most reactive, the solid or the atoms go into solution forming ions, and then salt bridge, double line. So we say this represents the phase, what we call the phase boundary, the boundary between the solid and the solution containing ion. The double line represents the salt bridge. And then now what will happen to the copper half cell here is that the copper ions will move out of the solution. So here zinc ions are formed, but here copper ions are discharged from the solution by gaining the electrons that are coming in this direction. So you have copper ions so they gain the electrons and then they move out of the solution as copper solid. So this will be now the cell representation. Now, since we have the voltage reading, you can always incorporate the voltage reading if you already have, but if you don't have, then you don't need to. So you just use the letter E. So for electrode potential, you use E. Then if it is standard, the sine theta will be there, so this we will discuss later. Since we have not used the standard conditions, so we leave it like that. So for our case, it was 0.9 voltage, so 0.9 V. So this will be our cell representation, including the voltmeter reading. Similarly, you can also be asked, apart from drawing this, you can be asked to write the equation, cell equation. Cell equation for the same. So in this case now, the cell equation, as I said, so here you take this as the reactant and this as the product, then you take this as the reactant and then this as the product. So zinc atoms on the plate or the rod will go into solution. So this will be, so zinc ions, so remember this are charged there, 2 plus, forgotten, so the ions you have to have the charge there, 2 plus. Then copper, the ions will come out of the solution forming this. So reactants on the left hand side, so the reactants will be copper, zinc solid plus copper 2 ions, aqueous, then product this and that. Zinc ions and copper solid. You can, so this will be the overall cell equation. You can also be asked to write half equations. At each half cell, what is happening? So you can be asked to write the half equations. Half cell equations. Then remember I said this, the zinc half cell will be now the negative electrode. So the negative electrode, we call it the anode. So this becomes the anode. So it is the negative electrode. And then the copper will be the cathode. So the cathode is the positive electrode. The cathode positive electrode. So the half cell equations for zinc half cell, that is the anode. So you have zinc atoms, they go into solution forming zinc ions, losing 2 electrons. And then for copper half cell, so the copper half cell will be now the cathode. So for the cathode, so the copper ions in solution, they will gain electrons. These 2 electrons that have been lost on this side, they flow to this direction, to the copper electrode, copper plate or copper rod. So they are gained. So on that side you have the gain of electrons. Then copper is formed. So now this will usher us to the next step. What will be observed? Observations at the anode and at the cathode. So apart from the half cell, so the next part is we discuss observations now, like in this arrangement. What observations will be made at the anode and at the cathode? Now let's discuss the observations that will be made at the anode and the cathode if we were to allow this reaction or this half cell to stay for quite some time, let's say maybe for 24 hours per day. So at the anode, as I said, what usually happens at the anode, so the anode, so this is the negative electrode. So an electrode is usually, by definition, is a solid conductor. Dipped in an electrolyte. So an electrolyte is a solution that allows current to pass through it, and it is decomposed by the same current. An electrolyte is a substance which allows electric current to pass through it and it gets decomposed by the same current. Now that is what we refer to as an electrolyte. So then the cathode will be the positive. So this one is positive electrode. So the positive electrode is the cathode, so in this setup. So the anode will be now the zinc half cell. So the observation that will be observed is that the mass of the plate, or if you use the rod, the plate or the rod decreases. This is what you will observe. So it decreases, while here the mass of the rod or the plate, depending on what you use, increases. So the explanation for this one is that zinc ion, the zinc plate dissolves, forming ions, releasing the electrons. On the other side, the copper plate, the copper ions from the solution gain the electrons, forming atoms which are deposited. That is why there will be increase. So what will be observed in terms of the solution? So here concentration of zinc ions increases for the same reason as above, because the atoms are going into the solution, forming more zinc ions in the solution. So the concentration of zinc ions increases. Here, concentration of copper ions decreases. And for this reason, there will be very conspicuous observation that you will see or you will make. The color of the solution fades. The color of the solution fades. So the color of the solution is going to fade on this other end. So those are the observations that you are going to make. So in this case, this will be the observations that will be made. Now, using different cell combinations, you can have a variety of observations. For example, particularly on the color of the solution. So just to take note of this, just take note of these three colored ions. The three colored ions. So these three colored ions take care if they are part of the electrochemical cell. Now, for example, if blue that is copper is on this side, then on the color of the solution you have to take note of that is going to fade. If it is now copper, like in this case, they are being discharged. The concentration of copper is decreasing. That is why the solution fades. But if copper was on this side, then you have a lesser reactive element like silver. So you have copper here, silver here. Then you see the concentration now of copper will increase. So instead of the solution fading, it will become more blue. The color of the solution will intensify. Same for iron. Now if you are using iron and then here it is colorless, so remember the color of these ions will intensify because of the increase in concentration of, now instead of zinc we are using iron, so the color will intensify. And just before I forget this, copper ions, some copper salts, but most copper salts are blue in color, but we have a few salts that are green, like copper 2 carbonate is green, copper 2 sulfide is green. So you can have a copper solution which is green. So green is not always iron 2. We have some copper ions that exhibit green color when they dissolve, even when they precipitate. So usually they take the color of the solution, except iron 3 ions form yellow solution, but when they are precipitated out, they form brown, precipitate. Then except now for the case of iron 2 sulfide. Iron 2 sulfide behaves differently. It forms a deep red solution. This one, iron 3 sulfide. So a little bit is the only unique one that forms such a different color. Red, deep red like blood. That will be iron 3 sulfide. But otherwise, most of iron 3 salts, those that are soluble, they form yellow solutions. But when it dissolves, it forms that precipitate. So when these colored ions are used, you have to take note. If they will be used as the anode, their colors will intensify. But when they are used as the cathode, as less reactive, the color of the solution will fade. For the others, the remaining the other metals, their ions are colorless. So it is difficult to state the effect on their solution because you will not see that concentration increase. But at least for these colored ones, when their concentration increases, the color intensifies. But when their concentration decreases, the solution fades. So you cannot take note of that. Then finally, so in the next lesson, our lesson number 6, we shall discuss the standard electrode potential. Now, if we remove one of these half cell and then we use the standard hydrogen half cell, the value that you obtain here, that value is called standard electrode potential. So like in this equation, we just stated E. So for standard, it will have that sign, meaning here you used a standard electrode potential, also standard conditions were observed. So in our next lesson, we study the standard electrode potential, that is the hydrogen. Then these values, when you have them, their uses, there is a lot that you can do with these values, and that we'll discuss it in our next lesson, lesson number 6. Thank you for watching, and those who are watching on YouTube, don't forget to subscribe.